Is it okay if I turn my camera on? There are too many things.
Sure.
Off, I meant. Let me see if I can. Well, this works. The students do the real work, and here they are. But when Abhishek calls you and asks you to do something, I have to do it. So here I am. What do you call him? Dr. Abhishek or Professor Abhishek? He has been doing incredible work in vertical lift. So I see his students all over the world, used to be at least before COVID when we went to conferences. And but this talk is for everybody, not just aerospace. Let me see if I can get the pointer. I also realized this is 6:30 in the afternoon. Used to be 7 o'clock was the dinner time in our residence halls. So I'm surprised so many students are here. I mean, we were lousy kids. I guess kids are much more serious and enthusiastic these days. So we learned a little bit about helicopters, carry everybody, a little bit about Mars, and then Mars helicopters, superficially at the top level, but there's more details in the slides for people who are more serious on this to pursue. I'm assuming the student's background is generic. In fact, the last presentation I gave was, let's see, was to Wall Street, and they were enthusiastic about it, although from their eyes, I realized they were probably getting bored. I was expecting, but now we have a more informed audience. So this is the helicopter. It's a typical configuration, and it generates lift using rotating wings. So for example, produces a thrust. The Black Hawk produces about 20,000 pounds. And so this lift balances the weight, which is why it hangs in air. But you remember from your high school that if you want to turn something, you have to put in a torque. And helicopters have enormous torque in the rotor system, about 10 to 100 times cars and trucks. So if you're trying to put this torque in from the helicopter, then remember Newton's laws, you're going to spin the other way. And to stop that, there's a little tail rotor that gives anti-torque. But there are many ways, many different ways to provide the anti-torque. You can have two rotors spinning in two different directions. And so this is why, unlike fixed-wing airplanes, which is more or less, by and large, the same configuration, you'll find many different configurations in aircraft. They're trying to cancel the anti-torque. And all of them are worse than the basic helicopter, which means they can carry less people, less payload with the same power, but they have their niche areas. So this is for heavy lift. Put them top of each other, it becomes very compact. You don't have to worry about the tail rotor. Side by side, you can go as fast as an airplane. And then there are other configurations that are neither here nor there, experimental versions. So many different ways to do anti-torque. But there's only one way to control a helicopter: by tilting the thrust vector. Like an airplane, there are no ailerons, no flaps, rotor is all you got. So you tilt the thrust vector, and a little bit of tilt does the job. Usually 1/5 the weight is all you need to fly forward. How do you tilt it? Well, the blades are not fixed wings. There are attachments at the root end that change the pitch of the blades. So as the blades go round and round, they're constantly moving up and down. So this little attachment that you can't see from far away, you have to come close to the helicopter, it moves up and down once per revolution and oscillates the blade. A typical rotor RPM is around 250 to 350, so 200 revolutions per minute. So every time the blade goes up and goes around, you're oscillating it once. And so 260 per rev divided by 60 comes out around 4 hertz of actuation. So not very high frequency, but it's a very energetic system and it's a very unsteady system. So these pitch lengths, how do they move up and down? Well, they're connected to something called a swash blade. One is rotating, one is fixed. And the fixed swash blade is connected to a very elaborate arrangement of actuators in the fixed frame, in the fuselage. So you don't need to understand the detailed load flow. Actually, Abhishek's PhD thesis was on that topic, but overall, it's an intricate mechanism and the blades are not fixed. And the main message is the rotor RPM, you don't want to touch it. It's constant. So this is how a real helicopter is controlled. So the first thing we learn is that Ingenuity is a real helicopter. It's not a drone or a toy. The RPM is fixed once and for all. And there are swash blades, 2 in fact, 1 for each rotor that is actuating the blades. The second thing to learn about helicopters is that if you plot the power versus speed, unlike an airplane, there is no stall speed because it can go all the way to hover. Even birds cannot hover. Well, except one bird, hummingbird. So you don't have in that part of the world, but in the North and South American continent, the western side, we have a few in Maryland. Hummingbird is the only bird that can actually hover. So hover is very hard. The message here is that hover takes the maximum power, not forward speed. So it's not like a car. Doing nothing, standing still in air is the most difficult mission. And so the original plan for Ingenuity, or the key criteria for success for Ingenuity, was to do hover. Hover, remember, is the most difficult flight. If there are people who are helicopter pilots in the audience, they will know what I'm talking about. It's easy to fly forward. You learn that first, but try to hover, it's very hard. So the blades are turning. One more thing we need to learn is something called the tip speed. So it's the speed of the blade tips as they go round and round. Typically, it's about 700 to 600 feet per second. So the tip Mach number, which is the ratio of speed to speed of sound, is about 0.7. So it's nothing dramatic. Airplanes, fighter aircraft fly at 2, 3 Mach. So it's a low speed. It's called low subsonic. But when it tries to go forward, then the blade that cuts into the floor, called the advancing tip, that adds the velocity. And all of a sudden, you hit the speed of sound. So in reality, when you see a helicopter, you may feel it's chugging along slowly, but it's the only aircraft that is designed to fly at transonic speed. Airplanes you fly in, they go subsonic, 0.85. Fighters go supersonic. No one wants to stay at 1. Only helicopters do it, and they do it once every, they do it 350 times, 300 times per minute. So it's a very unsteady environment, and it's very close to Mach. So the main message is you can't willy-nilly start spinning them faster. So you have to keep the tip Mach number in hover around 0.7. Or else there are unsteady shocks on the blades. It's just going to break your blades. So again, you don't need to understand what the shocks are, but just remember, you have to keep the tip Mach number less than 0.7. So while this is going on, the blades are also crashing into the vortices or little tornadoes created by the blades in front. You cannot see them unless you simulate them, but you can hear them. And that's what makes the sound, chop, 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 if you hear a helicopter coming into land. And so that's from where we get the name chopper. So now you have everything you need to understand Mars helicopters. A little bit of history. Um, the earliest reference to helicopter can be found in Chinese literature. And Joseph Needham and his graduate student Wang Ling have an excellent edition of transliteration of Chinese literature. So if you're ever interested, they have, I think, about 15 volumes. And one of the volumes are dedicated on physics and physical technology. And there is a clear reference to this kind of flying, they call it bamboo dragonfly. And the most fascinating thing is that it also warns that this account, I'll just read it, this account comes from the adepts and is handed down to ordinary people, but they're not likely to understand it. So it's not for normal people. And so it is very amusing that still today, helicopters are not taught in undergrad. It's a graduate curriculum. You need to understand aerodynamic structures, controls, to get into helicopters. But after this lecture, all of you will be in the category of adepts. The most modern reference, next time you go to France, search it out, they have the original manuscript, was Leonardo da Vinci's drawing. So many of you would know about that. So he's the Renaissance man. Of all the flying vehicles you can think of, there's only one that he drew and was fascinated by. And that was this little picture on the left of your screen. People considered that to be the genesis of at least the concept of helicopters. The person who coined the term was a French scientist, an engineer, and he coined the term helicopter. You can also see this in Paris. A replica, the original model is destroyed, but this is a photograph of the original model. It's a steam engine, it never flew. He just built it for demonstration, and he coined the term helicopter from the two conjugation of these two Greek words. The first flight, the first successful flight was by Breguet and Durand, also in France, but we do not consider it as a helicopter because it could never hover. Remember I said, we learned hover is the most difficult flight. So they could go forward, but they could never fly in hover. So yes, we credit them as the first flight of rotary wing aircraft, but not a helicopter. So what was needed was a crack pilot, because hover was impossible to fly. And the world found the pilot in form of the diminutive Hannah Reich. So all the ladies out there in the audience, this is your field. Without you, we couldn't have flown. So Henrik Fock designed this aircraft, and Hannah Reich first demonstrated rock solid hover. So Hannah Reich is an instance of ordinary people getting caught up in larger historical currents on the wrong side. But after the war, she made amends, and there is a rich history of her life and work. She spent a lot of time flying in Ghana, where she created a flying school. She flew Prime Minister Nehru over New Delhi after India's independence on a glider, because Germans still could not fly powered aircraft. And in 1951, President Kennedy invited her to the White House, and then she later settled and flew gliders in Appalachia, close to us, all gliders, because powered flight was out. Anyway, so that's the history of Hannah Reich. So that's the first successful helicopter, but not the first practical helicopter. That we give the credit to Igor Sikorsky. So the configuration you see now is due to Igor Sikorsky. The importance of Sikorsky is far more than just the configuration and controls, even the pilot sitting arrangement. He gave the creed for all helicopter designers, and this is a quote for him when he was trying to sell his idea to the Navy. And he said, the helicopter will be used for the next 100 years, not to destroy lives, but to save them. So Still today, the sound of a helicopter is a sound of relief. Of course, you can use any modern innovation to do all kinds of things, but that still remains the creed of all helicopter designers. That's the primary mission of any helicopter, to save lives. So with that, let's go to Mars. So this little thing on the screen is Earth. If your screen is not very clean, you won't be able to see it. And so this is how far away is Mars. It's a very cold, lonely, isolated place. Right now, I checked today morning, it's about 245 million miles away. It varies between 35 to 250. But there are close passes. And so every 10 years, there's a close pass and it would launch a mission. The Mars 2020 launched in 40 miles. The actual journey with all the actual trajectory is about 300 million miles. So that's a lot of miles. So far, there have been 50 Mars missions. One of the most interesting that are coming up is the Japanese mission. They want to land on Mars has two moons, Deimos and Phobos, and they're going to land on Phobos and try to return some sample. So very fascinating mission. These are the landers. Only there's a list of only the US landers, 4 of them, 3 of them contain rovers. We have landed all around Mars, all over Mars. You can look into these plots. This is also freely available on the internet. And the Perseverance landed very close to the inside, not too far away from Curiosity. The reason is this depression was formed, the geologists tell us, as a deep lake when a large object collided. And they believe there were hot springs that could have hosted life. So that's why we are interested in that area. So tucked under Perseverance was this little helicopter. And off we went. This picture, Abhishek, was taken by Andy Bernard. So instead of sitting there watching the liftoff, Andy is the vice president of Sikorsky, chief of design, all engineering design in Sikorsky. And he flew his own aircraft with his daughter just to say goodbye to the little aircraft while it lifted off. And then this on the right, all of you know that. So the first flight was 19th April. So now we are in Mars. Let's cover quickly these areas. Why? Well, in 25 years, rovers altogether, all of them have covered 44 miles. Flat, uninteresting terrain. There's no way to explore. You want to know why the recurring slope lineae appear and disappear, sometimes in weekly cycles, seasonal cycles, cliffs, slopes, ice flows. We know there's water now, hills, craters. We want to go into the deepest part of the terrain and take photographs of the cliffs, because that's where history and age is revealed by the creaks and cracks, right? Not only on human beings, but also on Mars. So that's what you want to explore. So it's compelling science is the term that's used by JPL, for which we need rotorcraft. So long ago, there were sketches. The first conceptual designs came out of HS competition. And this is a competition Kanpur students participate in. I think you won a few of them. I think the 24-hour hover competition, that was also Quack's rotor, I remember. And then it was carried forward to the detailed design, and you can read about it in this paper. This was the team. This is the obligatory thank you picture. And the most important point is that they gave the first blueprint for design. The biggest concern, all of you know, was the density. The density is about 1% to 2% of Earth. And so the question is whether you can fly at that very thin air. So I promise you, this is the only equation. And so you need to take your paper and pencil out and get a feel for it. So to be able to lift a mass against the gravity, so this force. You need density. You need the tip speed, square of the tip speed. It's a simple equation, so let's go through the terms. Square of the tip speed, the area of the lifting surface, so blade area, and another constant that you don't have to worry about, but it's an intrinsic, it's an aerodynamic, fundamental aerodynamic constant. It's not an universal constant. It's related to airflow. You have to have air. So the first question was, is that constant same on Mars? Because if it's not, it doesn't matter whatever you do. You can play around with the design, nothing will happen. And the principal contribution of the Maryland design was to say, yes, don't pay attention to density, look at viscosity. It is almost as sticky as Earth, so you should be able to fly. Engineers like to come up with a number for every physical quantity. So this number, viscosity, is characterized by a Reynolds number. And so the guidance the design gave is that there is viscosity, you can fly, just make sure you stay above 10,000 Reynolds number. And then you will have sufficient, that constant will look very similar to Earth. So that was the fundamental contribution of the Maryland design. Then there's an engineering challenge. So we're done with this constant, we're happy it's there. The density is, well, you fly in the morning, so you get as much factor out, still about 100. And the gravity, but the gravity is 1/3. So overall it's about 25 times more difficult. So your options are, you can have 25 times the blade area, which is ridiculous. There's no 25 times blade area. It's a huge blade area, means you can't even lift off. Or you have to have 25 times the tip speed square, which is 5 times the R. So 5 times 5 is 25. So those are your options if you look at this just naively. And even though the fundamental constant could be achieved, the engineering problem seemed unsurmountable 20 years ago, because you can't have 5 times the tip speed, because the speed of sound is actually lower than Earth. So sometimes you will hear people saying, oh, it's turning faster. No, it's actually turning slower. You cannot turn faster because the speed of sound is lower on Mars. So you can only probably turn 70% the speed on Earth. All right, so we are stuck with 0.7 here. 5 is out of the question. We can increase the area a little bit. So at least let's say 2 times. So 0.7 times 0.7 is roughly 0.5 times 2, that's 1. So this factor is a wash, same as Earth, which means everything falls on the structure. So you have to build a structure that is so paper light, using the properties on Mars that you can still fly. And the blueprint also gave a description of how to accomplish it, but it was just on paper. Anything can be shown on paper unless you build it. So subsequent to that, everybody forgot about the work. There was an attempt at NASA Ames to actually build and fly, but the rotor broke apart. And there was some analysis, but last decade, people in Japan has picked up the area in parallel with JPL's work, and JPL was funding us a little bit to look into different airfoils. And so if you want to know about the Mars helicopter, there is a lot of literature on it, all on controls and navigation. Aeromechanics is not really in public domain. The story is, while trying to control first as a drone, Howard discovered that you can't. It's a little bit of equations for Abhishek. Is the lock number is very, very low, which just means that there's no aerodynamic damping, and lock number is about 0.3. So that means if you put in a control, your blades will respond after 60 revs. And it just showed that you needed not only proper helicopter controls, but also a hingeless hub for adequate bandwidth. Otherwise, you can do the cyclics. The you won't get any hub moments. With all of that, it was ready to fly. So there's here's the top level comparison between the two. So overall, it's a 3.5 scale model that places at 1.2 kilograms. It's a little bit heavier because it's a hingeless hub. And the other numbers are, we were a little bit more cautious, but their Mach number is almost similar to Earth, but the tip speed is lower because for the same Mach number, the speed of sound is lower on Earth. So it's turning lower at a slower speed. This is the overall FACO, and you can read about it in Pittenberg's paper. It's listed there. So there are two independent rotor systems, two independent swash blades, because you can. So that's what you get from miniaturization of electronics. You don't have to come up with complicated interconnections between the rotors. Just make them two independent rotors. That saves some weight. The motors are special. So electrical engineers would like to know about them. The problem was heating. At night, it can be minus 100 degrees centigrade, but during the day, there is no air. So when you're turning the motors, how are you going to cool it? You can't possibly put liquid there on Mars, get frozen. So they came up with a Heatsink design, which is what limits the flight time. So when we say 1.5 minutes, it's because of the motor heating and other issues, but this was one of the main ones. But finally, it came down to the blades, because the blades size everything in the aircraft, and the blades are very carefully crafted to be ultra lightweight. So if you make a Mach scale model, and Abhishek will know this, this is about 1/10 the weight of any Mach scale model. So it's a very ultra thin blades. So you get a factor of 1/10 from each blade, and then everything flows down through the hub into the aircraft. So remember, you're trying to get a factor of 25. So the place you start from are the blades, because that decides everything. And so there were concerns whether the blades will fall apart. And at the time, we used the state-of-the-art aeromechanics solvers that were at the time built to analyze and design next generation tilt rotors. So that level of fidelity was brought to bear on the Mars helicopter. Actually, the students who did it didn't know he was working on the Mars helicopter. And I can't show you all the numbers, but so there is no spar. It's a sparless design, just tiny layups. And this is not very unusual these days for prop blades, advanced prop blades, but very, very thin. And you had to analyze those. Structural dynamics people, mechanical engineers would know that you could calculate the mode shapes. Only the first one is published, so it's here. No one can predict the mode shapes correctly, so you have to correct your materials, then you have to put on the Martian aerodynamics, and then finally get the stress plots on the blades. And those stress plots have to be cleared for flight. And so once you get there, you know whether your blades will hold. And so nothing is the final proof until you fly. And apparently she's flying around very happily, and there's no danger in horizon. But anyway, the stress plots told us how long we can fly safely. These are dynamic stresses. This is just a snapshot. So a quick summary. Deployment it's a small aircraft, easy to drop. The main difference is it's a hingeless hub. The swash blades are independent because you can, due to the advances in electronics, and two independent motors. In the olden days, avionics was in Stone Age. Nowadays, all kinds of systems based on sail mobile technologies, a small aircraft. But we also understood the limitations of the rotor design. So post-Mars, so the task for the future for you all is, so this is where we are. So twice Earth area, 0.7 square is 0.5. So this is a wash now. So the game is to see if we can push the tip speed to almost same as on Earth, which means it'll hit Mach 0.9 on Mars. Because I saw one of your speakers is Eric Greenwood, so no one knows more about noise than him. But there's nobody to complain on Mars. So the two of the biggest problems in helicopters, that is one of the biggest problems, is noise. Anytime you try to do something innovative, noise people show up. Well, there's nobody there on Mars, so let's push it all the way up so that you can get a factor of 2 here and relieve yourself on the structure side and then carry a payload. And so people have built models to try and figure out how to be able to do that, and have also advanced their simulation tools so we can get a better picture of what happens behind the scenes. And the main conclusion is throw away your art airfoils. They're no good on Mars. Turbulence is a friend. Get the flow separated as quickly as you can. So sharp-edged airfoils. And for example, this is the current Mars helicopter airfoil. Just replace it with a sharp-edged flat plate, cambered flat plate, and you get almost as good a efficiency of the rotor as the airfoil. So figure of merit is just a obscure way of saying how much power you need more than the ideal power. So the amount of power you're putting in, 40% is lost, 60 is what you're really needing to fly. So it's almost as efficient. And if you make it 2% thick, you save a lot of weight. The simulations have progressed to a level that, okay, even a simple model without fuselage, without 2 rotors can pick up the basic trend. But the 2 rotors passing over each other is of concern, particularly on Mars, where the pressure differences are very stark compared to the nominal. And you would have these spikes. Remember the city sigma, we talked about 0.15 as the maximum, but there's huge spikes on the blades as they move over each other. And these are, we don't know whether these are real because there's no test data, but at least simulations from academia and the Department of Defense agree. So at least there are big spikes. So it was a concern, but it's flying now. So one of the important things we learned was that the fuselage is there for a ride. It doesn't matter. It just doesn't do anything to the rotor, anything bad to the rotor. So which is a big deal for science people. It just means bring your stuff. We don't care which way it sticks out of the vehicle, and we'll just carry you to where you want to go. You don't have to worry about the shape and streamlining it like on Earth, because there's a very low drag, no density. So all of that folded into some of the concepts that are being evaluated for larger, more capable aircraft. So Ingenuity is a tech demo. It doesn't carry anything. Well, a camera because it keeps kids happy, but it really doesn't have any science payload. So there are these conceptual designs. It's freely available, and you can start looking at them. So we started here, and then we are trying to go back up to larger aircraft. 20 to 30, larger means still 20 to 30 kilograms of mass, but carry some payload. And one of the salient features of the design is that now people are exploring very thin airfoils and sharp with very sharp edges. So if you look at the report, you'll see many kinds of designs, but fundamentally, it's very thin, very sharp-edged airfoils. These kind of things won't do anything on Earth, but on Mars, they appear to work like magic. There is a lot of work done in Japan, which motivated this. They have actually looked at very thin triangular airfoils, and they have a special wind tunnel, a very small one, that can simulate Mars. So there is data for this kind of airfoils at very low Reynolds number and yet high Mach number. I think this is at 3,000 Reynolds number and 0.5 Mach number. And generally the simulations agree. If you're coming from a fixed wing world, you'll run away looking at this much fairer, but for helicopter people, uh, all right, you have to live with it. But both different kinds of predictions all agree. So we all have a problem, but the main contribution is that these airfoils behave very strangely. There is no drastic stall, and they just keep producing more and more lift. So you might be able to control them and even get more CD sigmas at these low Reynolds numbers. The challenge is 1% thickness. Can you really do it? Some people think, yes, we can. And there is a program now in NASA to try and actually build some prototype blades this thin and test it and see. And you can read more details in the paper. The next thing to learn is, of course, the blades have their attachment. And because it's very thin, the attachments are easy. It's not nothing exciting here. What is important for control system people is the control loads. And there is a problem there on Mars. The nature of the blades, the ultralight design, thin, and the layup of the spar is such that when you turn the blades, you have enormous moments on this control at the root. And the aerodynamic moment is nothing. So it's all from centrifugal forcing. And that's an enormous moment that shows up as a control system load. So what happens is you might come up with a wonderful controller, but you won't be able to actuate the blades. You'll run out of bandwidth. Remember, this is a tiny little thing. You can't put in a huge power conditioner there. And these pitch link loads can be 30% of the total lift, equal to the weight of the vehicle. That's not special to the next generation. Ingenuity has the same problem. That's why these little horns that you see are really nothing but counterweights. So you have to add some weight. This is just an additional ballast weight that is up there to help the control system actuate the blades. Remember, you have to push the blades up and down when they're flying. And that adds almost 1/5 the weight of the blade. And the problem is accentuated when you have thinner blades. So there are many innovations people are thinking about. One of them is to move the pitch axis. If you're on Earth, at this point, you should get up from the chair and leave because you do not want to move the pitch axis from 1/4 chord. If you put it at mid chord, you can show the unsteady aerodynamics. Torsion damping goes to zero, but close to zero. But on Mars, because their density is so low, it seems it will hold. But what it buys you is that if you move the pitch axis, if you place the blade a little forward, you drop the requirement of the counterweight. And remember, every ounce you save on the blade flows down to the whole aircraft. And then you have to carry this thing 300 million miles. So every ounce of weight is very important. So you could save counterweight. It's called Chinese weights or counterweights if you redesign carefully placed. And balancing the blade above the pitch axis also has other kinds of benefits. The stress concentrations that you get near the root, they're relieved. So, but the question is, without data, no one knows whether this is real. So in science, data teaches. You can do all the simulations and calculations, but unless you actually build and fly something and test it very carefully. So I'll leave it at that, some overall conclusions. So the problem is not low density. There is viscosity to bite into the air. The problem is the low speed of sound. And so the breakthrough early on was to recognize that, okay, there's enough viscosity to bite into, and Reynolds number is the key factor. Turbulence is a friend. Get the flow separated as quickly as you can. Martian flight is rich with all kinds of new phenomena. I tried to give a taste of all these. What you learned on Earth, not all apply on Mars. There are many benefits on Mars. So don't always focus on the difficulties and challenges. See what you have to gain when you design on Mars. There are no noise problems. In fact, vibration is gone because the wake is the core radius grows inverse to Reynolds number. So at very low Reynolds number, the vortices disappear. So the blades are not really chopping into very, very strong vortices. There are many benefits on Mars. And it's a fertile ground for research because there's no research data at all. There are some hover chambers available. JPL, of course, is a big chamber, but those are hover chambers, not really wind tunnels. And the Japanese wind tunnel is also small. It's hard. It's very difficult to make Mars wind tunnels because you not only need pressure, which is easy to do, but also temperature control, some kind of refrigeration system. Even if you ignore the fact that it's all carbon dioxide, that part you can ignore. And so just want to end by saying that it's a marvel and a miracle of modern science and technology that the aircraft that first flew on another planet looks remarkably similar to the concept from which the helicopter derives its name. So I'll end it with that. If the students are interested, there are a list of papers here that you can learn about the past, present, and future. Otherwise, thank you all for coming.
Thank you.
Dinner time.
Professor Anubhav. There are a couple of questions. How choppers score over fixed wing aircraft, particularly on Mars? This is one question. How choppers score over fixed wing aircraft on Mars?
So if you can keep the Reynolds number at 10,000, then you would be able to fly on Mars, but it's very difficult to pick up that speed. Of course, there's no runways, so you have to be launched from the atmosphere, but there's no way you can go inside a crater, hang like a bee near a wall and take pictures.
Absolutely.
So
That's
you can't accomplish in vertical lift things that it's impossible to do with fixed wing.
Good. There's another question. Would there cold welding issue in the joint of hub and rotor blade?
Yeah, I am not an expert on it, but I know that yes, temperature is a big deal, even for the blade materials. Composites have been tested down to very low temperatures, but they can become brittle. Yes, so those are concerns. So every time before flight, there is a period of time where you heat up everything, and you get signals beamed back to Earth that yes, things are working, everything is in working order, lubricated, whatever, and then you can fly.
Another question is, what is the energy source for the Ingenuity? How long can it hover?
It's actually pretty standard lithium-ion battery. I think Eagle Peacher makes it. It's a company in Connecticut, and they have been supplying lithium-ion batteries for NASA for a long, long time. So the batteries lie dormant during the 300-mile mission, and then they beam a little bit of data that we know they're alive. And the source is there is this solar cell at the top, and the solar panel at the top. So it takes, don't quote me on this, but I think it takes about 3 days to get the sunlight and then store your battery, store the energy in your battery, and then you fly. So that's also one of the limitations of 1.5 minutes, although there is a significant margin of safety. You probably can do 3 minutes.
Another question is, you said turbulence is a friend on Mars. Can you elaborate a little more?
You don't want laminar flow at very low Reynolds number because there is enormous drag and the separation bubble just does more damage. So you rather live with turbulent flow. And trips are hard. On Earth, whenever you need turbulent flow, you put some trips on the blades. Any little ounces of weight, so just make it sharp-edged. That is an area of research. It's not really settled, and there's very little data to make very conclusive conclusions.
Are you collecting vehicle flight data on Mars to validate predictions?
They are, yeah, not me. I'm in academia, but yeah, JPL will get back whatever flight data they can. Most of the flight data will be for um, the vehicle attitude and all of that. You cannot measure loads in flight. You can get the motor current and voltage, but that's about it. You cannot put a load cell in flight.
Okay. You said you have done the optimization blade according to the hover profile. What type of optimization? What is the criteria of this optimization?
So for any rotor, the criteria is, or any airplane, the overall criteria is lift drag. For rotors, that's all it was done. The actual Ingenuity aircraft, the rotor did not go through any formal optimization. It's just what we thought had the best shot of flight. So you minimize weight and maximize lift to drag ratio in any airplane. It's the same for rotors.
Any advantage to have swept forward or backward blade tip?
Seemed to us, it's a complication that didn't warrant to be on the aircraft. There are advantages on Earth. Most of it is to do with noise and vibration, and it kicks in at high speed. So in Mars, we're not really interested in flying in high speed. We're not trying to flee or reach somewhere quickly. So at low speed, no.
Nice. You have gone to the Mars before going to Moon. Any reason?
And, well, no, it's a good question. If Earth is destroyed, it'll take the Moon down with it. But Mars is a separate entity. We're talking about science fiction, but those are dreams. There was atmosphere, I understand, 2 billion years earlier on Mars. We want to know why it went away, and if there's any way to bring it back.
Okay. Could we have morphing blades?
Sure, if you build it and show. I mean, packaging. No, I mean, packaging is a big deal. You can't send aircraft like that. So at a very minimum, it has to have a static morphing so you can put it in. So even the hexacopter picture I showed you, if you look at the NASA report, a lot of effort went into how it will fold and go in. So even if you're not morphing in flight, so in helicopters, you dream of morphing because the requirements for hover is very different from high speed. But if you're not interested in high speed, very high speed, then.
One observation, twist at root is visible in the picture. Is it a result of optimization of blade to get a desired L/D ratio?
Yeah, the twist is not unusual. The plan form is a propeller-like, so I don't like it. Also, the tip is rounded, which it's just because it came out of a prop code. Helicopter tips, you never want them to be rounded. You want the tip vortex to be formed in a clean way. So those are all refined next generation. I think the chord changes very dramatically, and because there is a circular blade cuff, it looks a little strange. But the twist is just like any other helicopter twist.
Here, which component of the system is determining the life of the Ingenuity? Is it a bearing or a rotor system, or which is the one? Any comment?
Well, the battery life won't let you fly for too long. There's also the motor heating issue. As dynamicists, we were worried, because there's no damping. So anytime there's a perturbation, there are high gusts on Mars, right? Low gravity means high gusts. So anytime there's a flat perturbation on Earth, it dies out just right away. On Mars, it'll keep oscillating. So the blades are continuously under fatigue load, even though they're in hover. That was just a concern for us, but that was not the criteria for 3 minutes, or 90 seconds is half of 3 minutes.
Maybe we have time for a couple of other questions. One question is, why don't you select variable speed motor to fly instead of fixed RPM?
It works for very tiny aircraft, but the blade frequencies are very carefully placed. And already there is no aerodynamic damping. If you hit a resonance while you're changing the RPM, you're gone. These are not plastic blades that you can fool around with. So you do not want to touch the RPM. Even for the hexacopter, it's a collective control. It's not an RPM control. So general rule, starting point, don't touch the RPM. I know you guys play around with it on Earth, but even on Earth, when you're scaling things up, you don't want to make RPM the variable.
No, you chose this coaxial rotor in place of multi-rotor. Yeah. So you had looked at both, but you finally chose a coaxial rotor.
So overall, the coax with 2 blades per rotor is the minimum weight that balances the blades, balances the weight, balances the torque, and gives you the maximum Reynolds number. That's why it's a coax with 2 blades per coax. Apparently, people figured that out 100 years back when they were trying. But anytime you have more blades, your blade Reynolds numbers are going down.
Primarily, it is the weight, final weight.
Yes.
That is the kind. There was one team which is working on designing blades for rotor to descend in Venus environment. Is there any specific suggestion of aerofoil series to start with?
You have to talk to them. That's an APL mission, not a JPL mission.
Yeah.
People in Penn State are working hard on it. So Abhishek, next time you can ask Ed Smith.
Thank you. Wonderful to listen to you and wonderful to listen to your answers to a large number of questions. Thank you very much. Abhishek, okay, anything else?
No, I mean, that is all I think. I mean, there are so many nice, interesting questions from students. And,
Yeah.
it's really nice.
Let us thank.
As always, I mean, listening to Anubhav is, I mean, such a refreshing experience every time. Okay. So thank you so much.
Great, an extraordinary clarity in the presentation. Extraordinary clarity. Thanks a lot, Professor Anubhav. Thank you. Thank you very much. Thank you.
So you have other presentations following me, right? There's another.
Yes. Now, so there is another presentation from Srikanth Saripalli. So he'll be talking about the vision investment. Oh, he's already just joined. Okay. So,
can I also watch it, or do I have to register?
Yeah, please do.
No, you can absolutely.
All right.
You can take your slides off so that we can.
So I'll just put up the slides. So we are ready for our next speaker. So
yeah, I hope Srikanth is there.
Yeah, he's already joined. Yeah, he's already there.
Yes, there. Okay.
Yes,
so
I'm here.
Yeah, good. Good to see you, Professor Srikanth. So nice to be here. I like to, of course, a lot of people, most of the people who are in this field know you, but let us tell our friends, young friends. Professor Srikanth is the professor in Mechanical Engineering Department and is the director for Center for Autonomous Air Vehicle and Sensor Systems at Texas A&M University. And he holds the Gulf Oil Thomas Career Development Professorship. And he has a lot of interest. But he also works on air and ground. That is what I'm very happy to see that. But one thing I'm very happy to see is you have an interest in developing low-cost autonomous air vehicle that could be used for enabling scientists. But what you are going to tell not only for scientists, for others also. What if you do a low-cost autonomous air vehicles? I don't want to take too much of time to explain. Your biodata has been already known to people, and we feel very happy and privileged to have you as a speaker here. And especially the topic, what vision-aided autonomy for VTOL UAVs is a very critical one, very, very critical one. And we look forward to listening to you. Could you, thank you very much for agreeing. May I request you to start your presentation?
Thank you. Thank you very much. Thank you for asking me to present. And I know this is the last talk, and it's 9 o'clock, and it's 8 o'clock, 7:30. So I will. I'll try to make my talk a little bit more, let's say, have a lot more videos and a little bit less on equations and things like that, so that it's more fun. So let me preface by saying that I'm not an aerospace engineer, right? So I'm a roboticist. I do have an undergrad in mechanical engineering, but I consider myself a field roboticist. So when I look at autonomous vehicles, particularly VTOL, so my PhD was on autonomous landing for helicopters. But when I look at it purely from a autonomy perspective, not a aerospace engineering perspective. And there are two reasons I want to start my talk with that is because, first of all, if I say something that is that's probably not the current wisdom in aerospace, so forgive me for that. But again, I'm thinking about it more from an autonomy perspective and not from an aerospace perspective, right? So the low-cost UAVs, I don't have slides on it because I was going to specifically talk about vision-aided autonomy, but I'll tell you a story. So the reason I was interested in very, very low cost, and when I mean very low cost, I'm talking literally less than $100. This is because before I moved to Texas A&M, I used to work a lot with geologists and oceanographers. And they usually use these UAVs for scientific purposes. And they typically take them to places where you do not even have a Walmart or any of these stores to buy basic parts, right? So the question for us was not how efficient could you build an autonomous vehicle, but really what can you build so that you can get information. So really the way for them to think about this is, I want a camera in the sky, or I want a magnetometer in the sky, or I want a air sampling sensor in the sky. And I'm going to be in the middle of nowhere, say Atacama Desert, or I'm going to be near a volcano, and things are going to crash and things like that. So what are all the things that you can remove out of a vehicle so that you can make it fly and give me the data? So we were not looking at it from an efficiency perspective. We were purely looking at it from a, how can we get something to fly so that somebody can get data, and how can we do it so that you could use rubber bands and you could use duct tape and things like that to do that. But that's for a different talk. I'm going to talk about vision specifically, and vision for autonomy, and why I think vision is probably one of the primary sensors that we want to use for autonomy, right? So this is I found this a couple of years back, and I'd like to start off with this because this is, I think this is an interesting story about robotics and autonomy, right? And I might be wrong, but the first autonomous vehicle use is about in 1849. The neighborhood kingdom of Venice, they wanted to invade Venice. And so the king basically talked to all his scientific advisors. And they came up with this contraption, if you want, on the right that you see here, which is basically a bunch of balloons. And their idea was to carpet bomb Venice, right? So the idea was that all these balloons are connected by a wire, and they have explosives on it. And they thought at the appointed time, they would fly all these balloons. And when it came, they would pull one of these things. And so they would carpet bomb Venice. And so they would take over Venice instead of actually going there and fighting, right? So if you are a roboticist and if you work in the field, your well-known plans usually don't work, right? Your well-laid plan. So what happens is that, of course, they all forgot about air. There was a wind that blew. So this wind, basically, those balloons, instead of flying over Venice, they basically flew back into Austria. And then, so instead of carpet bombing Venice, they carpet bombed Austria, right? So it's a very interesting thing if you're in field robotics and if you're trying to make autonomous vehicles. A lot of times, things that you kind of expect will go. So it's very important to understand assumptions, right? And so when you start thinking about vision and when you start thinking about how you can use vision for doing things, vision is a great sensor, but I like to tell people that vision works very, very well till it fails. And when it fails, you have no idea where you are or what you're doing, right? So vision, when you're building systems, you always want to think about vision as aiding something that you're doing rather than being the only sensor that is used, right? So I kind of want to talk about why vision, right? So on the left, you see standard inertial and GPS sensors, and on the right, you see, say, Lidar, radar, and other sensors, right? So vision somewhere in the middle, right? So as you go from, say, your inertial sensors and GPS sensors, you get increase in amount of information accuracy, but compared to Lidar, you have decreasing cost and size requirements, right? So there are a lot of things that we can do with vision, but the biggest problem with vision is that you do not get scale, right? But the nicest thing about vision is that the first thing that you do as soon as you build a vehicle, you have a quadrotor or a hexacopter, is you put a camera on, right? So if you can solve things with the camera, then that's very helpful because you're always constrained by your size, weight, and power requirements, right? So that's how I want to think about it. Now, a majority of what I'm going to talk about is how you can use multiple visual sensors so that you could do collaborative either localization or navigation for these VTOL UAVs, right? So specifically for quadrotors, that's what I'm going to talk about. But before I do that, I wanted to kind of take a small detour and kind of talk about some of the things that we've done with vision, which I think are very interesting. And I wanted to kind of present them from a perspective of, hey, this is what we've done, rather than kind of saying about the techniques that we've done. So again, the reason, so this is one of the recent NVIDIA challenges that we've done. So the reason why I'm showing you this is, if you start thinking about why vision, right? If you have, so this is data collected by NVIDIA from several different kinds of UAVs flying around. And the idea was, the challenge was really asking the question, how well can you track objects of interest, right? So the red is the actual ground truth, and the green comes from what our algorithm is doing, right? But if you think about it, for a lot of things that you want to do, vision provides the right modality for doing these kinds of things, right? And so again, similarly, so one of the first things that the reason why I got interested in thinking about vision was I was fascinated by autonomous landing, right? And autonomous landing for helicopters is something that people have been looking at for a long, long time. But I was fascinated from it from a sensing perspective, is could you actually land a helicopter on a moving target, and not just a moving target, a target that's pitching and rolling, right? So this is very useful, particularly in oceans when you're trying to land on a Coast Guard ship and things like that, right? So what you see here is one of our early attempts at doing this. So we have a downward looking camera, and the downward looking camera is looking at a target, and this vehicle's moving, right? What it's doing is using a single monocular camera, it's actually calculating the roll pitch yaw of the motion of the vehicle, and then also calculating the XYZ motion of the vehicle. And then there's a closed loop controller, a higher level controller, which is controlling the velocity of the vehicle for land, right? One of the things, so this was one of our early attempts at doing landing, and we've been trying to make it better. One of the things that we realized after we did these is that the harder part is, the much harder part is not just the landing itself, but to figure out when to actually abort landing, right? So if you have, if there is a slight disturbance, so let's say this vehicle is moving and there are potholes or things like that. So at some point you have to kind of determine, well, I'm going to land right now, and I'm going to, or I have to abort. And then I'm going to go back and search for this particular landing target to land. So, and that becomes fairly hard. And we don't have a right way, a principled way of doing this right now. We have some heuristics on when you determine how to land, depending on what the roll and pitch angles are and things like that. But then you're kind of getting into heuristics of doing it rather than trying to come up with a principled way of doing this, right? Similarly, so this is again, recently there's been a lot of work on using, on doing obstacle avoidance for quadrotors, right? So this is some of our initial work where we were doing this using a combination of LiDAR and vision. Adding LiDAR to the system makes it much nicer. So this is work that was done probably about 10 years back for really with Carnegie Mellon University, where we were looking at how can you do high-speed obstacles. So this is about 10 meters per second doing this, right? So these are, this gives you kind of like an idea of some of the things that you could do with vision. So I really want to talk about two things right now. One is how can you detect other UAVs when you are in a UAV, and I want to kind of probably go a little bit more deeper into how you do that. And then the second part of it, or the major part of the talk, is really about how you could do what when you have multiple of these vehicles, how can you localize using those multiple vehicles? And then how can you actually do path planning using multiple vehicles so that you're maximizing some information, right? So let me first talk about the first one. The problem that we got interested in for a long, over the last couple of years was to look at how do you detect other smaller UAVs from another quadrotor, right? If you're trying to detect larger vehicles, then there's lots of research that's been done on object detection using fairly standard computer vision techniques or learning-based techniques, and there are various sensor modalities for doing this, right? But our question was really, so if you have these small quadrotors that are flying around, can we use the image sensing information that are coming from depth sensors? And the nice thing about if you're using a depth sensor, so kind of like a one of the Intel depth cameras, RGBD cameras, is you get position information, right? And so using that position information, the objects are easily distinguishable from the background because of disparity. So, right? And so can we use that to detect these, how well can we detect other fast flying quadrotors using this, right? So here, what you see, the top one is just an image. The top one is a quadrotor that's flying. This is an image from another quadrotor, and the bottom one is a disparity image, so a depth image of the same thing. And as you can tell, it's actually very easy to distinguish this quadrotor from the background noise, right? That led to us to ask the question: can we do this? And can we do this where we don't have to actually? Can we do this for different kinds of quadrotors? And can we do this using a learning methodology? And instead of gathering a lot of information, real life data, can we do this somehow using simulation, right? So, and can we test that then so that it become better, right? So there's this fairly nice simulator that's from Microsoft. It's called AirSim. Actually, the interesting thing is we have a project with Bell right now, where Bell's interested in looking at urban air mobility, but Bell's also working with Microsoft so that they can expand AirSim to bigger helicopters. So there's some interesting work that Microsoft is doing on basically aerial vehicles, right? So what the simulator is really using the Unreal game engine so that you can get good environmental maps out of it, right? And from those environmental maps, and you can't see the second image here, but the first image, the left image, kind of shows a model of a quadrotor. This is a parrot drone flying in a city kind of environment. The middle image kind of shows a depth image. So there is a quadrotor here, which you can't see. And then the right one kind of shows that using those depth image, you can actually figure out where the quadrotor is, right? So the nice thing about this is we did not have to go out and get a lot of data, right? So again, going out and getting data means that you're spending a lot of time actually getting good data. But if you can get this data from a simulator, then you don't have to go out and do this, right? So we got lots of data. So basically, we wanted to generate data that actually replicates. So we have this stereo camera system that you can see here. It's really a fairly simple system. It has 2 cameras. It's fairly lightweight. And so we can generate depth data out of that. So we wanted to emulate that and generate depth data using the Microsoft AirSim. So we have AirSim that gives us RGB pairs, and then we could do stereo matching, and then we can run a fairly standard deep learning model called YOLO. So once we have a model that detects this, right, we can get real life data from our stereo camera, and from that we can actually detect bounding boxes for the drones that we are detecting, and we can actually say with confidence what we are detecting, right? So we trained quite a number of these. So this is about 200,000 of them. But the bigger question that we wanted to ask was, of course, we are training this in simulation. So how well does that work in real life, right? And so one of the other question for anybody who's worked on stereo is that the problem with stereo, of course, is that your baseline, the distance between both the cameras, kind of determines how far you can see, right? Particularly if you're doing this on a fairly small drone, the baseline is probably set to about 6 to 10 centimeters, not further than that, right? So if you want to see far enough so that you can avoid these vehicles at higher speeds, you want to see at least 5, 10 meters, ideally as far as you can see, right? So one of the things that we are very interested in is to kind of say how far can we detect this and how well can we detect this, right? So our detections are about 9.5 meters, right? And how quickly can we do this, right? So using a NVIDIA Jetson with a stereo camera, we could do this at about 10 hertz, and that is nice. So I'll show you a couple of videos of this. So what you see here is there's a vehicle here, there's a vehicle here, there's a flying around, and then you have a vehicle here hovering. And then the question is, how well can you detect these drones when they're flying around? So this is the proof of concept. It kind of says you can do this fairly well, and at rates that are relevant if you're trying to do obstacle avoidance, or if you're trying to actually use this in a real life scenario for doing this, right? Let's see. this is the same one, just showing things moving around in different direction. So that's nice. So you could use vision for doing obstacle detection, obstacle avoidance, things like that. So, but over the last couple of years, one of the things that we've been interested in is, so if you want to use vision as one of the sensors, of course, you typically end up using vision for doing things like either object detection or maybe things like 3D maps, things like that. But because you have this camera and this camera is free, can you improve your localization accuracy? So not just the position of the vehicle, but also the attitude of the vehicle by using this camera. And there's been a lot of work on this, right? So things like visual inertial odometry, people looking at visual odometry using cameras, but then we wanted it to move it a step further, right? So our question was, what if you have multiple of these, right? And if you have two cameras on each one of them, of course, you can think of them as separate vehicles and then kind of say the question, ask the question, can I improve my localization accuracy? But what if you think of them, both of these vehicles as connected with an invisible rod, right? So an invisible thread. So then this becomes a variable baseline stereo, right? Of course, one vehicle could drop out, another vehicle could come in. So you have multiple of these, right? So now because cameras are kind of free for us, right? So can you now think of this as a stereo payload? And can you improve the accuracy, the position, the attitude of each one of these vehicles when these vehicles are moving around doing their own thing, right? So I kind of think about it as a variable baseline stereo, right? Stereo is two cameras that are fixed, but now you have two cameras that are moving around all over the space, and then you'd like to use that to kind of figure out and improve the accuracy of your localization, right? And then of course, the next step then is a more interesting question, which is like, if these vehicles are moving around, can you now force those vehicles to move in specific ways so that your accuracy of whatever you're looking at is improved, right? So there's the localization aspect, and then there's the planning aspect of this. So I'll try to explain this in one slide, and then I'll move on to showing videos because I think they're much, they're cooler. But let's say you have N MAVs, right? So you have N quadrotors in a group, right? So this is, you get images from the first quadrotor from 0 to N, right? So you're getting these images. You could do feature detection on them, right? And once you have detected features, you can match those features. You can remove the features that are not good, right? And then you can compute a relative pose. And this is fairly standard in computer vision technology, computer vision terminology. So this is really bundle adjustment to figure out what the pose is, right? So the biggest problem here, of course, is that you have no scale because you're using a single camera, right? So I get one image right now, and after some time, I get a second image. I match features between these two images. I remove the features that are not good. And because I can match features, then I can compute a relative pose, right? But the problem with this, of course, is I have no idea of what the pose, what the scale of these features, this pose that are computed is, right? Oops. But now I have multiple UAVs, right? So I could pick from the first one, the second one, I could compute features. I can solve what's called the PNP corresponding problem. And that also gives me metric poses for all of the different UAVs, right? So once I can initialize my scale based on these poses. So if I have two vehicles that are looking at the same scene, and I know they are the same scene, I can compute the actual pose between these two vehicles. And because I know that, I can actually now initialize this part with this part. And then now I can create a 3D map, which is actually has scale in it. And that gives me what the pose of both these vehicles are, right? So there is a intra-camera estimation and there is a inter-camera estimation, and I could do both of them based on heuristics or based on well-known. So when do I do inter-camera estimation? I want to do this as fast as I'm getting images. When do I do intra-camera estimation? Whenever I think my covariance is getting bigger or I'm losing my knowledge of where these poses are, I could do this intra-camera estimation. And so I could do kind of keep on doing both of them. And that allows me to actually back out my attitude and position information, right? So this is all great, but how well does that work in real life, right? So what I'm showing here is there are two UAVs. These are manually controlled, right? And they have an inertial measurement unit on it, but we actually want to calculate what our roll pitch yaw are using our vision-based estimation. So this is both inter and intra-camera estimation, right? And then compare that to the IMU estimates that we are getting out of this, right? So if you see, we are flying these UAVs all around the place. They're just randomly being flown. There's not, I mean, they're looking at a structure, but it's not really relevant what that structure is because they're tracking basically features, right? And what you see in this graph, what you see are the roll and the pitch angle, right? And the estimates actually match what you get roll and pitch angles from the initial measurement unit. We are about less than a degree in roll and pitch from the initial measurement unit, right? So there, of course, this is great, but so let's see if I can show you. And this shows the position. So that was about attitude, and this is showing the position. So again, you're flying these quad rotors all around the place. And then, of course, you'd like to get your estimates of how they're flying. So this kind of tells you their XYZ positions and for doing this, right? So this is nice, but a caveat being, of course, they need to track some features. So if you're looking at an empty sky and if you want to fly them, this would not work, right? The second caveat being, this only the update rate of how quickly you can do this is really the rate at which you can grab images, right? So if you're only doing this at 30 hertz, then your estimation rate is only really at 30 hertz. And so 30 hertz is good enough higher level control, but if you're trying to do attitude control and things like that, you really want to be running this at higher speeds, right? And there are cameras that go at 100 hertz and things like that, but then suddenly your cameras go from $100 to something of the order of $1,000 or more than that if you're trying to get these high-speed cameras, right? So this is great for high-level planning, control, but not so great if you're interested in doing low-level attitude control, things like that, right? So, so the question, so we kind of said, well, we won't answer the second question, which is, can we update these localization estimates at a higher speed, right? So we are okay with 30 hertz, but we try and answer the first question, right? So, which is, how do we make sure that these cameras, really these UAVs, are always looking at features and they're always looking at good features, right? So that we get good estimates of position and attitude, right? So, oops. So the question that we want to ask is, we want these vehicles to move in such a way that vision-based localization is always possible, right? And we want this so typically, if you think about typically people who work in autonomy, you have perception, you have planning, you have control, right? And all these are considered different, right? But once you get to a point, you realize that you want to combine all three of them. If you want to build these things that are actually going faster or they're actually more robust, right? So here, our idea is, well, we're not control engineers, so we're not going to worry about control, but we are interested in combining perception and planning, right? So what you're looking here, and this is a toy example, is let's say there's a house here, and let's say you have 3 quad rotors, right? and they need to go to these 3 points. They're starting at this point and they need to go to these points, right? So if they just flew path 1, path 2, path 3, now these baseline distances is pretty hard. So these dotted lines kind of show their field of view, right? And so while you can do this, if you're trying to do this using vision-based localization techniques and things like that, what happens is that you lose your localization, right? So we can't localize if you're not looking at the same features and we are not looking at nice features, so you can't do this. So the idea then, of course, is what if instead of them moving on this red line, we actually can force them to move in this blue way, right? So what this does is that because each one of these vehicles has this field of view, so this vehicle is moving in such a way so that it maximizes the features that it can see, but it's also maximizing the features that vehicle 1 can see with respect to vehicle 2, right? So in that way, it's actually improving the localization estimates, right? And then to do this, we also need to come up with a path planner so that it actually forces the vehicle to move in this way, right? So what we are saying is construct trajectories so that your quad rotors are always moving in a way so that you're maximizing the localization instrument, right? So really, when you're thinking about this feature-based estimation, so we want to build a 3D map, and the better the 3D map is, the quality of your your localization is increases, right? And then, of course, you want to track these 3D points through images, right? So the first point, of course, quality of 3D map depends on if you have 2 vehicles, how well do you know their the position estimation between these 2 vehicles, and are they looking at good features, right? Now, if you think about a single vehicle, how well can it track these 3D points, right? So the first one is between vehicles, so intra, and the second one is in a single vehicle, so that's inter, right? So we had a two-phase approach, and I want to make sure. So, okay, I have about 7 minutes for doing this. The first one that we call is next best view, right? So which is given that you have multiple vehicles, how do these vehicles fly so that they're always looking at a best view, right? And then the next question is, can you make them fly better, right? So you want to use vision-aware planning for individual vehicles so that they're always now able to track better features, right? So the first one, make sure that these 2 vehicles are flying better so that you can get better 3D maps, and the second one, make sure that you're actually flying them so that you can track better features, right? So then there's of course the question of what defines a good set of waypoints for map reconstruction, right? So now we are talking stereo. If you're talking stereo, features that are too far off, they're not very useful, right? So you're looking at texture, you're looking to get dense point clouds of it, right? So this is really what's called as next best view for multiple vehicles, right? And then, so there are lots of things that you can think of, right? So there's feature overlap, there is span of the features, how are they all through the camera, there's visibility of the features, no collisions, so that's the other one. You want to keep a minimum baseline, then you want divergence angle, things like that, right? So if you take all of these, you can come up with a cost matrix for this, right? As it turns out, this cost matrix can give you an objective function, and you can then kind of say, well, now I want this objective function to be minimized, right? So what you're seeing here is basically, if I have 3 vehicles in this particular format, there's occlusion here, they do not have a good enough baseline, so this a cost matrix J1, while this has a cost matrix J2, and ideally you want to drive your vehicles towards J2 rather than J1, right? So we want J to be low, except that thinking about this is in a 4n dimensional space is highly nonlinear and very, very hard to model. So because we don't know how to model it, and we don't know how to find derivatives for this, we tend to think of this as a black box optimization problem. And we solve it using a sampling-based approach. We basically use a particular algorithm, and this is in our papers, but we solve it. And that gives us, let's see if I can play this. Yeah. Oops. No. Okay. I think I'm missing one or two things. But really, so if you start from this X and Y positions of the drones, and this is the partial 3D map of it, what you're looking for is you want these drones to actually move in a direction so that your objective function actually your objective function is minimized, right? So in this particular way, the objective function is minimized. The way that happens is that you want to move in this red direction so that it happens. Okay. So you could do this, and really, so what you're looking at is how do you do this using, say, the main factors that involve this are the point cloud density. So if you have nice point clouds that you could get, then those are nicer. And then if you have localization error, that's also nice. Now, if you can think about number of vehicles, right, and path cost constraints. So if you have 2 vehicles, then you want both of them to be like this. If you have 3 vehicles looking at the scene, you would like them to be in this particular way. You can add more vehicles to this. So then they can be spread out in this particular way. You can also think about path cost constraints. So if you have more paths, if you have specific kind of path cost constraints, so things like you want to drive in a particular path, right? So you do not want to be near a particular path. You don't want to go into a particular area. You want to avoid obstacles. You could show that basically how these path cost constraints actually influence your depth error. So you want to make sure that your depth error is not too much, but you also want to make sure that you're able to actually use these cost constraints, right? So that we could do that. So the next step, of course, is, okay, that's great for multiple vehicles, but then I have a single vehicle. Not only do I need to make sure that I'm moving with the second vehicle, but I also want to make sure that I'm tracking the right set of features, because if not, I can't actually localize myself, right? So now you come back to doing this on a single vehicle, right? So you've done it with multiple vehicles. And then again, it's the same goal. So if you're going from start to goal, and these show error ellipses, right? Of what do you think your localization error is? And so maybe if you want to go here, the right way to do this is to actually do this, because by moving on this blue path, you reduce your covariance, so you get very good localization, and then you can do this, right? So for that, we have a sampling-based algorithm, which we call vision-aware rapidly exploring random tree. And so the idea is fairly simple. You sample randomly from your position and yaw. You then steer to that existing node because you already have a map. You can project your 3D points, and then you can check for visibility of that. And so you could create a sampling-based algorithm, except that instead of trying to minimize path cost, you're trying to minimize your localization error, right? So most sampling-based algorithms, they look at path cost, or they look at, say, even control effort. Here, we are looking at how do you reduce your localization error. So, and of course, I won't go over it, but this happens to be something that you do in belief space. And so you can come up with your cost matrix that you could add you have a path cost, and then you have a cost based on your covariance matrix, right? So if you set this to 0, which means you don't care about how good your features are, your cost just becomes your path cost. And then if you're doing a sampling-based planning, that is a fairly simple, any kind of sampling-based planner can be used for that, right? But now you have a path cost that's based on your covariance matrix, right? Then there's an interesting question, of course, of how you calculate this covariance, right? So, and that's the crux of the problem for this, is because you're trying to get good features. And what do you mean by good features? The way we have thought about it is that once you take these features in your 3D map and you project them onto a 2D plane, then your reconstruction error should be small, but then there are other ways to do this. Either way, depending on what you mean by big features, you can come up with a covariance matrix. And then once you have a covariance matrix, you can come up with a trace of the covariance matrix, and you can use that to calculate a path cost. And using that path cost, you can now come up with a sampling-based planner. So for example, what you see here is the 3D map, right? This comes from flying from multiple. So this is, let's say, a building. These are your point clouds, and you want to now fly your quad rotor from your start to goal position while minimizing your localization error, right? So you start, you go this way, but of course, now if you would like to move in this direction while actually turning so that you can see at more points, these are the more points, so there's not enough points here, and then so you can maximize your localization, so minimize your localization error, and then you can come back to your goal position, right? So this is great, but this is kind of like a discrete algorithm, so you do not get smooth trajectories out of it. So you want to combine this with the minimum snap trajectory generation algorithm so that you can get feasible trajectories. So you could take this as your initial algorithm, and when you combine that with the minimum snap trajectory algorithm, you get the smooth algorithm that you can use, right? And that allows you to do things like actually avoid obstacles, right? So here, what you see is a small entrance, right? So you want to start from here, you want to end here, and you're flying. You want to avoid this obstacle, but you also want to orient yourself in a particular direction so that you're getting the best localization estimate possible, right? So let's see if I can show this. So this is basically, you're trying to fly from one location to the other location. This is the building. This is the reconstruction of the building that you have. And when you have that, you're moving in such a direction so that you're maximizing this your localization, and this results in smooth trajectories that are in position and yaw space, right? So oops. Let's see if I can clear this. Yeah. So again, you started at a particular position, you're trying to go to another position. So what you see here is on the middle graph is the position where you have started. You want, and I'll let this play and then I'll talk about it. So really what you want to do is to go from this position to this position over here. But if you just moved in this direction, you would not, your localization estimates would be really, really bad. So what you did is you went towards the building so that you increase your localization estimate, and then you came back so that then you could achieve your goal point. Right. So I am out of time, so I will stop here. But before I stop, so broadly, what I wanted to kind of give an overview was that having vision kind of gives you this extra degree of freedom in your sensing space, so that you could think about interesting problems where you want to maximize, say, your localization or your object tracking, and or finally you want to use vision for as an aid for your control, so that you're you're doing something else, right? So typically you have your quad rotor, and the quad rotor is typically being used for doing something else. And that could be a scientific mission, that could be a geologic mission, that could be a search and rescue mission. And most of these times, you end up using visual sensors for doing that. And so can you incorporate that vision into your planning, into your localization, into your control space? And one of the, I think the novel aspects is that instead of thinking about it from a single vehicle, can you think about it from multiple vehicles so that we could do this, right? And I will stop here and thank you very much. And I am happy to take any questions.
Thank you, Professor Srikanth. It's an extraordinarily wonderful talk. There are a few questions here. I will choose and let you know. Let me start from the beginning.
Oh, I can see the questions. If you
want, you are able
to
see?
Yes, I'm able to see the questions. I can go through them, and if I miss something, you can tell me that I've missed it. So the first question is for tracking. Are you using the usual YOLO algorithm? Yes, it's a slightly different one because this was for a specific competition for NVIDIA. So and they had requirements. There were two requirements. It was not just the tracking accuracy, but it was also a requirement about how much power do we use for running this tracking algorithm, right? So if you ran an algorithm with a very high number of nodes, then you would end up using a lot more power, right? So we had to modify it a lot. So for the second question, for obstacle avoidance, what is the threshold distance for LiDAR to work? So that's a very good question. So this gets into sensors. So for us, so if you tune so most LiDARs don't give you this, but the LiDAR that we were using for this was a special LiDAR. So if we fine tune the LiDAR, so if you increase the power of the LiDAR, what happens is we would end up detecting dust. And then your helicopter would try to avoid dust. So it would start doing all kinds of weird things because it would detect specks of dust, and then we were clustering it. So we don't have a good, nice answer based on, say, any kind of theory. But really, the way to think about it, and I don't remember the exact number, is you want to fly at 10 meters per second. And so to fly at 10 meters per second, your LiDAR's at about 5 hertz, and your planning algorithm, and there's a minimum reaction time for the helicopter flying at 10 meters per second. And so you can back calculate what is required for the threshold for the LiDAR to work. For us, for avoiding wires, the wires were 6 millimeters thickness. And so I think we were looking probably at about 30 meters, right? And if you think about it, a 6 millimeter wire at 30 meter distance looks exactly, very, very, very tiny. And so a lot of times if you have dust particles or things like that, then and if you have a couple of them, you would think of that as dust, right? What is the reduction percentage you need to get from similar confidence score when taken from airspin compared to actual test image data set? So we do not have an actual test image data set because we were lazy and we did not want to go out and collect actual test image data sets, right? And I don't know of another data set that is available to actually answer the question. But using something like AirSim, we did not have to collect any real image data set. So we basically trained a complete algorithm in simulation. Could Movidius yes, Movidius is a viable alternative. We have been looking at Movidius. As a side note, the problem with Intel is that they randomly scrap their CPUs. If you've heard, they've stopped making RGBD sensors now, and just because they're not making any money. So we are always afraid of using something that Intel tomorrow morning could say, no, we don't want to do it because we don't have any money. We are not making any money out of it. So yeah, but definitely Movidius is an alternative. How can we do localization, autonomous navigation in a GPS denied system? So a lot of what you see these days uses something called visual inertial odometry, VIO. So monocular camera looking downwards with inertial measurement unit. So the IMU provides you kind of like the initial scale factor. And then also when you're doing fast yaw roll pitch, can tell you where to look for features, right? So the IMU aids you in that. And then the current state of the art gives you less than 1% error per. So if you have traveled, say, 100 meters, your error is less than a meter in terms of position. So this is not SLAM. So this is pure odometry. And there are several techniques that do that, particularly for aerial vehicles, right?
So are these techniques, sorry to interrupt here. So the what you mentioned, I mean, are these primarily meant for indoor applications or they are also okay for outdoors?
They're okay for outdoors. They're, I mean, they're always, like I said, vision works till it fails. So, I mean, if you're using vision, you're kind of assuming that there is decent contrast, not too dark, like your quadrotor is not pitching so much that you're looking directly into the sun. And those are the times that your IMU aids in it. So you're basically double integrating your IMU. But if you do that for a long time, I mean, these are cheap IMU. So you can't really do much. But I mean, you could think of interesting things. So you could have one camera looking sideways and the other camera looking sideways. So you could think of like if the vehicle was pitching up, then there's another camera that doesn't look directly into the sun. It looks in the opposite direction. So you could look down, right? But VIO is now fairly, I wouldn't say standard, but there are lots of open source implementations. There's OpenVince, which is nice, I think. It might not be the best, but it's the most well-documented and also probably one of the top 3, top 5 best things. And it gives you about a well-tuned VIO will give you about a less than a 1% distance error. I don't know. I haven't seen Spider-Man movies. Because I don't know which I'm not a big fan of Spider-Man, so I don't watch Spider-Man movies. What is the metric to decide what features are good? That is a great question. We do not know what that metric is. So you come up with, so like I said, we kind of say good features are, so if you have multiple vehicles, you're looking at things like, are the features all over the imagery? Do they have enough distance between them? Then are they contrast? So most of the times you're looking at contrast for features. So you're basically calculating gradients in the X direction, Y direction. And then if the gradient is different enough, sufficiently different enough, that's a good feature. But that depends on, there are some newer techniques that use deep learning to learn features. And so then there's a question of how do these techniques actually learn these features? And then, so that's a different question. Have you tried this for swarm formation flying? Yes, so for collaborative localization is formation flying, not really formations, but really looking at how to collaborate. So we still think of them as separate vehicles, but when they come together, can the vehicles be used together to increase the localization accuracy of both the vehicles, and then they can go back and do their stuff, right? So they're loosely coupled. How well does YOLO handle occlusions? Not well. So, I mean, it's just one of the algorithms that we use. It's a simple algorithm, but there are way better algorithms right now. That was 2019. So this is, in the last 2 years, there are much better algorithms to do deep learning. If I want to detect beyond that, what other techniques can be used? Say I have to detect typical capacity. Radars will work. There are some cheap radars that you can use for doing this. So the biggest concern is weight. Like if you could put if you could put 2 kilograms, then there are radars, there are lidars that you can put. But if you're trying to detect something 100 meters away, you're still stuck with vision because there are no high resolution sensors that can detect at that distances, that small objects, right? So if you have a drone that's a hexacopter 100 meters away, the angle, so even the best LiDAR right now will not, there's not enough resolution on your LiDAR to detect that. Radars can do that, but then the antenna for the radar will become too big because your azimuth and elevation angle sweeps need to be too big. So you have to use cameras. So the 9.5 meters is really using stereo, but you could do something similar with monocular cameras and high resolution cameras. So then the problem is your compute power. How much can you do computation on board? So what kind of GPU can you put on board? And there is some interesting things that are happening with 5G. So 5G really promises, if you do microwaves, 5G on band 260 promises less than 10 milliseconds and greater than gigabit per second, which is amazing if you consider it, particularly for UAVs and drones. We have a project with AT. So I do not believe those numbers, even though everybody has told me that those numbers are true. So I'm not a network specialist, but so you can transmit data to to the ground station. You could do a lot of processing on the ground station, and you can transmit back stuff to your UAV. Previously, that was not possible with 4G, with microwave, because latency and bandwidth considerations, right? But if what they're saying with 5G is possible, then you could do that, and then there are some interesting things that you can do. But 5G, I think, is still in the nascent stages where true 5G is not available anywhere. It's all people talking about 4G, LTE, and things like that. Even with multiple cameras, when you don't know the baseline between them. So I was hoping somebody would ask this question. So we cheat. So at some point, we need some initialization of scale at just once. Whether you can do that using GPS at the beginning, when you start off, you could do that by looking at a known feature. We actually look at windows and we kind of say, we know windows and doors and the size of those or things like that. But we need it only once, either when you initialize the system or somewhere in between when you start off the system, right? So there's an interesting question here that I think from a systems perspective is very interesting. You have camera images coming. How do you synchronize these camera images, right? Because one camera could be at a different space and the other camera could be running, it's on a different computer and both have different clocks. So this is where GPS comes in. Even though this is GPS denied, GPS is very useful for timing information, not position information. And timing works even if you have just one satellite, and you need it only, again, once or twice. So because GPS time is accurate up to nanoseconds. And so you could synchronize your cameras based on GPS time rather than, so when you get that, you could synchronize your clock on your UAV based on the GPS time and then not have GPS for as long as possible, right? Did you use centroid location to track? No, this was just a helipad. So there was a hitch painted on that, and we were just using that. What is the added difficulty? I think the big difficulty is finding the roll pitch yaw and then tracking the velocity, the position and velocity of the target. We used to find good features, but yes, that would work. Could you specify some algorithms to handle occlusions? Yes, graph. I don't know on top of my head any graph algorithms that would work. But again, I'm not a deep learning person, so I do not know what the state of the art is. How much of it is practical? Power and weight penalties, which is lower in flight time compared to other measuring setups. So I don't agree with that. I think the biggest power for any vehicle, whether it's quad rotor, whether it's ground vehicle, is motors. Compute power is tiny. And you always put a camera on a vehicle, even if you don't know why you want a camera. That's the first sensor you put. So cameras are free, right? I think as Professor Datta was saying, science wants sensors, but even if you take anything that you put, you strap a camera on it because it's cool. We all like camera images. We want to see images, things like that, right? So I consider cameras as free. And yes, there is a compute penalty, but compared to other like motors and other sensors, cameras are not, yeah, the compute penalty is tight. Using Pixie, tend to wonder what is difficulty while landing, say, on an oscillating aircraft carrier. That's a good question. You should see on YouTube. There's a nice video of a helicopter landing on an aircraft carrier at ocean states of 4 or 5 or something like that. So then the ocean is pitching. So pilots can't land. The way they do it is they put an anchor down, and so they couple the aircraft carrier to the helicopter and land. And you should see that. It's very, very scary. And Coast Guard is the most scariest, not Navy, things like that, because they go when the ocean is very bad, and then they try to rescue people, and they're trying to land. So it's very, yes, Pixie works, and but the controls, the dynamics are much, much harder. How will your system work at night? That's a good question. So remember that cameras are, you could, if you think about the electronic the spectrum, visible cameras are 400 to 700 nanometers. You can think of thermal cameras, IR cameras. You can think of ultraviolet cameras. These are all cameras. So there's nothing, yes, some of the techniques might change, but there's not that different that's going to happen, right? So the bigger question is, will they work during fog? Because none of these sensors work nicely during fog or dust or things like that, right? So yes, this is, again, that is why the title of the talk was vision aided, not just vision, because you always want to think about them in terms of aiding. Good. Okay, I think I answered all the questions.
You answered all the questions. Thank you.
I have one
mindful to
I have one last question actually for you. Yeah. So we are looking at a very peculiar problem where we want to detect some movements below a forest canopy. And we are hoping to use Lidar for that actually. Okay. So we did some experiments with Velodyne Puck, and it is really bad. Okay. So do you have any suggestions? I mean, what could be a better sensor? I mean, a better Velodyne or some completely different sensor?
So it's a very, very hard problem because
actually, yes.
Most, I mean, everything. So I don't know if you're using the dual returns from Velodyne. Velodyne has dual returns. So not only, so ideally what you want is a full waveform LiDAR, but full waveform LiDARs are $500,000, and they're like 50 pounds or 100 kilograms. So there's no way to get that. So I would try, I mean, it is a really hard, maybe like there are some new startups in radar, like what they call 4D radar. So not like Bosch or there's a startup called ARBE, but they're all startups, so I don't know if you can get them. So, but really what you're trying to say is, can I look under the canopy and can I get some information? If I can get some information, then I can use it in some optimizer to actually make some predictions, things like that. But if you can't see anything, then there's nothing that you can say.
No, I mean, even simpler, actually, we are thinking, I mean, we have a human in the loop who actually looks at the point cloud coming out from the LiDAR and makes out that, I mean, is there a living thing, or is there an animal? Is there some human being or something?
Look at, I mean, thermal can't go through complete canopy, but overlaying thermal on LiDAR might help a little bit, because thermal can, the heat. Humans are very, I mean, we can, like, maybe there's something like if they're under leaves, then the heat content changes, things like that. So definitely thermal would be one thing I would look at. Right. And instead of, if you have, I mean, again, it's a cost perspective, but instead of like long wave thermal, I would look at medium wave thermal. So which is nicer because it can detect water better, but nobody sells medium wave thermal. Most of them are ITAR. I mean, even in India, mostly they're for DOD. I used to work for CARE, so I know that it's not something that you can get like just, it's not something that you can buy.
Okay. Yeah, got it. Thank you so much. Thank you.
Thank you.
Thank you.
So
thank you very much. Yeah.
So we had a very good couple of, both the talks are extraordinarily good, and we are enriched by the inputs and by the thing. And we have come to very good, and all the questions, almost all the questions that have been put have been answered. I think it has been wonderful. So thank you all. Thanks to both the speakers, and thanks to Abhishek and the team, which is coordinated the whole thing. Thank you.
Thank you, Dr. Kota, for hosting this session. And thank you so much to both Anubhav and Srikanth to sparing time out so early.
I totally missed your talk. I didn't see there was a page 2 in the announcement.
That would have been, I mean, really early in the morning for you, actually.
It's a 6 o'clock, yeah, a little bit, but I would have enjoyed it over a cup of coffee. But anyway, I can talk to you later separately.
Sure.
Okay. All right. Thank you.
Thank you very much. And thank you all the listeners who have stayed till almost 9 o'clock at night to listen to these exciting talks. So thank you very much. Yeah. And people in USA, you have a great day.
Thank you. Thank you so much. Yes.
Thank you. Thank you all.
Thank you all. Thank you.